Good day, everyone. We are Group 9, and today we will discuss geological structures and engineering significance. Our presentation focuses on three major geological structures: folds, faults, and joints. These structures may naturally occur beneath the Earth's surface, but they greatly affect the safety and stability of engineering projects such as buildings, tunnels, bridges, dams, highways, and foundations. As future civil engineers, understanding geological structures is important because even the strongest structure can fail if it is built on weak or unstable ground. By the end of this discussion, we hope you will understand how geological structures influence engineering decisions and why geological investigation is necessary before construction. Now, let's begin. Before constructing any engineering project, engineers first study the condition of the ground and rocks beneath the surface. Why? Because geological structures control rock strength, groundwater movement, slope stability, and earthquake hazards. For example, a tunnel may collapse if it passes through fractured rock. A dam may leak if joints and faults are not identified. Buildings may crack or settle unevenly if foundations are placed on unstable formations. This is why engineering geology is very important in civil engineering. Understanding folds, faults, and joints allows engineers to reduce construction risk, improve structural safety, and prevent costly failures. In short, geological structures directly affect the lifespan and integrity of infrastructure.
Now let us study geological structures more closely. Geological structures are features formed within the rocks because of the forces acting inside of Earth's crust. These forces create what we call deformation. Deformation refers to any change in the shape, size, or position of rock materials due to stress. Rocks respond to stress in three different ways. The first is elastic deformation. This happens when rocks temporarily change shape but return to their original form once the stress is removed. Second is plastic deformation. In this case, rocks bend permanently without breaking. This usually happens deep underground where temperature and pressure are high. Third is brittle deformation. Here, rocks fracture or break because the stress exceeds their strength, and this is commonly occurs near the Earth's surface, and these deformation processes are responsible for forming folds, faults, and joints. Geological structures are divided into two major groups: primary structures and secondary structures. Primary structures are structures formed at the same time as the rock. Examples include bedding, ripple marks, cross-bedding, and lava flow structures. These features help geologists understand the rock's original condition before the deformation. Secondary structures are developed after the rocks are formed, and they are caused by tectonic stress and deformation. Examples include folds, faults, joints, foliations, and lineations. Secondary structures are especially important in engineering because they can weaken rock masses and create hazards during construction.
Now let's move to our first major geological structure, folds. Folds are bends or curves in our rock layers caused mainly by compressional forces inside the earth. Instead of breaking, the rocks bend slowly over millions of years. Folding commonly occurs during tectonic plate movement and mountain building processes. Folds are important in engineering geology because they influence slope stability, groundwater flow, excavation safety, and tunnel construction. Folded rock layers may contain weak zones that can become unstable during excavation. Engineers must carefully study folded formations before construction roads, tunnels, or foundations. There are three common types of folds. First is the anticline. An anticline is an upward arc-shaped fold. The oldest rocks are found at the center. Engineering-wise, anticlines may create unstable slopes because fractured rocks are often concreted near the fault hinge. Second is the syncline. A syncline is a downward fold shape, like a trough. The youngest rocks are found at the center. Synclines can collect groundwater, which may increase seepage and water pressure in tunnels and foundations. And third is the monocline. A monocline is a step-like bend in otherwise horizontal rock layers. Monoclines create uneven ground conditions that may complicate foundation and road design. Understanding these faults helps engineers identify possible construction hazards before building begins. Folding occurs because of different geological forces acting on rocks over long periods of time. The main causes include first, compressional forces. When tectonic plates push against each other, rocks become compressed and bent. Second is plate movement. Mountain building activities often create large wall systems. And for the third, high temperature and pressure. Deep, deep underground conditions make rocks softer and more flexible. And for the fourth, differential stress. Unequal forces acting on rocks can produce bending and deformation. Now let's discuss the effects of faults on engineering projects. Folded rock layers may cause landslides, unstable foundations, tunnel collapse risks, and groundwater problems. Because of these risks, folded areas often require additional reinforcement and geological investigation, which increases construction costs.
Moving on to faults. Faults are fractures or breaks in rocks where movement or displacement has occurred because of tectonic forces inside the earth. These movements happen when stress builds up in the crust and causes rocks to crack and shift along a fault plane. Faults are important in engineering geology because they can weaken the ground and affect the stability of structures such as buildings, roads, bridges, dams, and tunnels. There are several main types of faults. First is the normal fault, where the hanging wall moves downward relative to the footwall due to extensional forces or pulling apart of the crust. Second is the reverse fault, where the hanging wall moves upward because of compressional forces. Next, a thrust fault is a special type of reverse fault that has a low angle shape and can move large masses of rock over long distances. Another type is the strike slip fault, where movement is mainly horizontal, such as the San Andreas fault. Lastly, the oblique slip fault combines both vertical and horizontal movement. Understanding these types of faults helps engineers identify possible hazards and design safer structures. Faults have a major engineering significance because they directly affect the strength and stability of rock masses. Rocks near fault zones are usually fractured and weakened, making them less reliable for supporting structures. This is a serious concern in engineering projects such as dams, tunnels, highways, and building foundations. Faults are also associated with earthquakes and ground rupture. When movement suddenly occurs along a fault, it releases energy that causes seismic activity. This can damage structures, roads, and other infrastructure. In addition, faults can increase seepage and groundwater movement because the cracks and fractures allow water to flow more easily through the rocks. This can lead to leakage problems in dams and water tunnels. Because of these risks, engineers perform detailed geological mapping, subsurface investigations, and monitoring before construction begins. They study the location, activity, and characteristics of faults to avoid dangerous areas whenever possible. If construction near a fault cannot be avoided, engineers must design structures that can resist or accommodate possible ground movement to improve safety and reduce damage. Fault zones are areas surrounding a fault that can contain crushed, broken, and weathered rocks caused by repeated movements along the fault plane. These rocks are much weaker than solid, intact rock, making fault zones unstable and hazardous for engineering projects. One major hazard of fault zones is that they are more prone to landslides and erosion, especially during heavy rainfall or earthquakes. The weakened rock can easily collapse or slide downhill, threatening nearby structures and communities. Tunnels constructed through fault zones may also experience serious problems such as water inflow, rockfalls, and deformation of tunnel walls. These conditions can increase construction costs and create safety risks for workers. Foundation built near fault zones may crack or settle unevenly because the ground is unstable and may shift over time. Active faults are especially dangerous because they can generate earthquakes and sudden ground displacement. This can severely damage buildings, bridges, pipelines, and transportation systems. Because of these hazards, engineers carefully investigate fault zones and apply proper reinforcement, drainage systems, and monitoring methods to ensure the safety and durability of structures.
Now, let's discuss joints. Joints are fractures in rocks where there is no major displacement. Even though there is no movement, joints are still very important because they weaken rock masses. There are different types of joints. Systematic joints. These are regular and parallel fractures. Non-systematic joints. These are irregular and randomly oriented fractures. Tectonic joints. These form because of tectonic stress. Cooling joints. These develop when lava cools and construct. Exfoliation joints. These form when pressure is released from rocks near the surface. Joints strongly influence slope stability, excavation safety, and groundwater movement. Joint patterns and spacing. Rocks rarely contain only one joint. Usually, joints occur in interconnected networks. Joint sets. These are groups of parallel fractures with similar orientation. Joint systems. These are multiple intersecting joint sets. Joint spacing refers to the distance between adjacent joints. Closely spaced joints weaken the rock mass by dividing it into smaller blocks. Another important factor is persistence. Persistence refers to the length or extent of a joint. Long continuous joints pose greater engineering hazards because they create larger failure surfaces. Understanding joint patterns help engineers evaluate rock stability and excavation safety. Influence of joints on engineering. Joints have major effects on slope stability and excavation. In slopes, joints can create several types of failures. Planar failure. Blocks slide along a single joint plane. Wedge failure. Blocks slide along the intersection of two joints. Toppling failure. Steep rock columns rotate and fall forward. Joints also affect underground excavations. During tunneling, jointed rocks may cause rock falls, tunnel overbreak, and groundwater inflow. Highly jointed rocks often require reinforcement methods such as rock bolts, shotcrete, and grouting. Without proper support, excavation in jointed rock can become very dangerous. Engineering applications. Now, let us connect geological structures to real engineering applications. Foundation stability. Engineers study rock structures to determine whether the ground can safely support buildings, bridges, and other heavy structures. If the rock mass contains faults or highly jointed zones, foundations may become unstable, leading to settlement or cracking. Tunnel construction. Knowledge of faults, and joints help engineers choose safer tunnel alignments and reduce the risk of collapse. Tunnel orientation is also important because excavation through fractured rock can lead to rock falls and groundwater inflow. Dam and reservoir safety. Faults and joints beneath the dams must be carefully identified and sealed to prevent seepage and leakage. If ignored, these weaknesses may threaten stability of the interdam structure. Slope stabilization. Structural analysis helps engineers design retaining walls, drainage systems, and rockfall protections measure for highways and mountain slopes. Groundwater control. Geological structures influence groundwater movement, which is important for excavation, foundation design, and underground construction. Overall, proper geological investigation helps engineers create safer, stronger, and more efficient infrastructure projects. Importance of studying geological structures. So why is it important for civil engineers to study geological structures? First, it helps engineers identify safe construction sites. Second, it allows engineers to design stronger and more stable foundations. Third, it helps prevent engineering problems such as landslides, slope failures, tunnel collapse, seepage, and structural damage. Studying geological structures also reduces construction risk and minimizes future repairs and maintenance costs. Most importantly, understanding the condition of the ground helps protect both human lives and infrastructure. This is why engineering geology plays a major role in the success of civil engineering projects. To conclude, geological structures play a very important role in engineering geology and civil engineering. Faults and joints influence slope stability, groundwater movement, tunnel safety, and foundation performance. If geological conditions are ignored, engineering structures may experience cracking, settlement, landslide, or even complete structural failure. That is why proper geological investigation and structural analysis must always be conducted before construction begins. As future civil engineers, understanding geological structures will help us design safer, stronger, and more durable infrastructure for society. Thank you everyone for listening. The information used in this presentation was sourced from reliable books, journals, and academic references on structural geology and engineering geology. Thank you once again, and that ends our presentation.